In an organic reaction, chemical bonds have to be broken in order that new compounds may be formed. The breaking of the chemical bonds is called cleavage or fission. Homolytic cleavage occurs in non-polar bond involving atoms with similar electronegativities such as the chlorine molecules. Okay, so in chlorine molecules, the single bond here, it got two electrons. It will break symmetrically where these two atoms will get one unpaired electron. So it will break symmetrically, right? And it will form two chlorine radicals. To show the bond breaking in the homolytic cleavage, we are going to use the half-headed arrow. Indicates that only one electron is moved from this single bond. Okay, so this chlorine atom will get one unpaired electron, and also this chlorine atom also get one unpaired electron. So the chlorine with one electron here is what we call as radicals. So radicals is the substance with an unpaired electron. While in heterolytic cleavage, it occurs in a polar bond involving unequal sharing of electron pair between two atoms of different electronegativities. For example, here if I have hydrochloric acid, the HCl molecules, okay, so there is a difference between electronegativity between hydrogen and chlorine atom, alright, so when this happens, the single bond will break unsymmetrically where the more electronegative atom will get both electron. Okay, so since hydrogen more electropositive compared to chlorine, okay, so the two electrons here will goes to chlorine. Okay, so now we are going to use a double-headed arrow to show that the two electrons is moved to chlorine. Okay, so what we get here is the cation. Okay, so the hydrogen, since the two electrons goes to chlorine, so now the hydrogen got no electron, so we have H plus and an ion Cl minus. Okay, because the chlorine here got an extra electron comes from hydrogen, so we have cation and an ion formation. Let's take notes on some of the arrow types that is being used in chemical reaction. So the first one here we have the arrows for a one-way reaction, okay, where reactants converted into product in one-way direction. Okay, so this arrow we are going to use for the equilibrium where we have a forward and reverse reaction. Okay, this arrows is for the resonance structures, and this arrow to shows the movement of an electron pair. So we are going to use this arrow to show the movement of electron, usually in the heterolytic cleavage. And then the last arrow here is for the movement of single electron. We are going to use it for homolytic cleavage. When the carbon got one unpaired electron, we call it as a carbon radicals. So for the carbon radicals, it can be designed as a primary, secondary, and tertiary, depends on the number of alkyl group that attach to the carbon atoms that bears the unpaired electron. For example, here, okay, so I have the methyl radical because there is no carbon attached to this carbon radicals. But then for the second one is the primary carbon radicals, because the R group here is the alkyl group. Okay, so since it has one alkyl group attached to it, so it is a primary carbon radicals. The secondary carbon radicals got two alkyl group attached to it. The tertiary one got three alkyl group attached to it. So the stabilities of the carbon radicals is depends on how many alkyl group that attached to it. Okay, so since the carbon radical is an electron deficient species, so it lacks of electron, so the kekurangan electron, so it will have a low electron density on that carbon. So the carbon radicals will be stabilized by the presence of the alkyl group. Since the alkyl group is an electron donating group, okay, so it will donate electron towards the carbon radicals and makes the carbon radicals more stable. So as the number of alkyl group increases, the stability of the carbon radicals also increases. So let's have a look at this example. List the following radicals in order of decreasing stability. So we are going to arrange it in order of decreasing stability. So first, let's check our carbon radicals. Okay, it's the type of carbon radicals that we got here. Okay, so for this carbon, right, for this carbon, there is two carbon beside it. So this one is the secondary carbon radicals. And then for this carbon, okay, for this carbon, we have three carbon next to it. Okay, on the carbon radical here, we got three carbon, okay, attached to it. So this one is the tertiary carbon. And then the last carbon radical that we got here only got one carbon attached to it. So this one is the primary carbon. So to arrange it in order of decreasing stability, the one that is more stable is the one that got more alkyl group. So since here got three carbon, okay, so the three carbon here is referred as the alkyl group. Same goes to here. We have two carbon next to the carbon radical, so we have two alkyl group. But then this carbon only got one alkyl group. So the one with the most alkyl group attached to it is the most stable. So let's label it as my compound A, followed by secondary, and then the least stable is the primary carbon radicals. So to arrange it, okay, so we have A, B, C. Okay, so decreasing stability of radicals. Heterolysis of a bond to carbon atom may produce a carbocation, which carbon with the positively charged, and also carbanion, which carbon with the negatively charged. Same like carbon radicals, the stabilities of the carbocation is depends on the number of alkyl group that attach to it. So the type of carbocation, okay, so first here we have the methyl, where there is no alkyl group attached to it. If we have one alkyl group attached to the carbocation, then it is a primary carbocation. Two alkyl group attached to the carbocation, it is a secondary carbocation. Three alkyl group attached to the carbocation, it will become a tertiary carbocation. So carbocation is also an electron deficient species, which is it is lacks of electron. So the electron density on the carbocation is very, very low. So it will be stabilized by the presence of the alkyl group, since the alkyl group is the electron donating group, where it will donate the electron towards the carbocation and increase the electron density on this carbon. So as the number of alkyl group increases, the stability of the carbocation also increases. This question asks us to rank the following carbocations in order of decreasing stability, classify each as primary, secondary, and tertiary. So before we arrange the carbocations that we got here, it's better for us to identify the type of carbocation presence. Okay, so for compound A, so let me highlight this carbocation and then just have a look at on this carbon, how many carbon that are attached to it. So for this carbon, we can see that only one carbon attached to it. So this one is the primary carbocation. So we have the primary carbocation here. Okay, and then for this carbon, for compound B, okay, so this carbon got two carbon attached to it. Okay, so it is a secondary carbocation. Okay, so we have the secondary carbocation, and then for the last carbon, the last compound here, right? So since it is in a condensed structure, so kita ada bracket dekat sini, it is better for us to open the structure first. So we have CH3 and then C plus, and then we have a branch CH3. Remember the bracket shows the branch, okay, and then we have CH2 CH3. So from this drawing, we can see clearly that this carbon attached to three carbon next to it. So it is a tertiary carbocation. Okay, so this one got 3 alkyl group, this one got 2 alkyl group, this one got only 1 alkyl group attached to the carbocation. Okay, so to arrange it in order of decreasing stability, okay, since the number of alkyl group is directly proportional to the stability of the carbocation, okay, so compound C, alright, C is the most stable, followed by compound B, secondary, okay, 2 alkyl groups, okay, and then the least stable is the primary. So if you arrange it, okay, and then state that the arrangement here is the decreasing stability of carbocation. For the carbanion, the positively charged carbon states that this carbanion is rich of electrons. So carbanion is an electron-rich species. So it already has a high electron density on this carbon. So the alkyl group will destabilize the carbanion. So the presence of alkyl group will destabilize the carbanion. Okay, so as the number of alkyl group increases, the stability of our carbanions will be decreased. Alright, so let's rank the following carbanions in order of increasing stability. So as the number of alkyl group increases, the stability of the carbanion decreases. So we have to find the carbanion with most alkyl group attached to it. So first let's identify the type of carbanion. Okay, so for this carbanion, so since it has 2 carbon attached to it, so 2 alkyl group, so this carbanion is a secondary carbanion. Okay, so next we have this one. Okay, so since there is 3 carbon next to it, so 3 alkyl group. Okay, so this one is the tertiary carbanion. And last but not least, we have this carbanion, only 1 carbon attached to it. So it is a primary carbanion. Okay, so to rank the following carbanions in order of increasing stability, the one with most alkyl group attached to it is the least stable carbanion. So the tertiary here is the least stable carbanion, followed by secondary, and then primary carbanion is the most stable carbanion. Okay, so arrange our compound in order of A, B, C, increasing stability of carbanions.